Welcome back. Confidence intervals on correlations. You can calculate an R value for any scatter plot, and that R value is a descriptive statistic for the linear component of the relationship between X and Y. But usually we want to do inference. We want to regard our 106 students as a random sample from some population of students, and these 106 data points as a random sample from some underlying population distribution. To justify the calculation of confidence intervals that we'll make, we need to assume that that underlying population of X and Y values, X and Y pairs of values, has a bivariate normal distribution. That's a generalization of the normal distribution to two dimensions, hence bivariate. Here are a couple of pictures from a bivariate normal population. Here we have a large sample of data points from a bivariate normal distribution with correlation of 0.6. Now, what is a bivariate normal distribution? Well, it's an infinite distribution of potential data points. If we dropped all these points down onto the x-axis here, we'd have a normal distribution of X values, and if we drop them sideways down onto the y-axis, we'd have a normal distribution of Y values. Now think about a single value of X and all the Y values for potential points above it. They in fact would have a normal distribution of Y values like this. At any other point along the x-axis, there's a similar distribution of potential Y values. Now we have to assume homogeneity of variance of Y at every different value of X. In other words, as we slide this point along the x-axis and look at all the various distributions of Y, all these distributions have the same variance, the same standard deviation. The amount of variability in Y is the same at each value of X. And similarly, in a bivariate normal distribution, we have homogeneity of variance in X, meaning that if we look at this distribution of X values at a particular value of Y on this Y-axis, then we slide this line down to other values of Y, and at each one of those values we look at the distribution of X, then we have the same standard deviation, the same variance in all those distributions of X, no matter which Y value we choose. So that's homogeneity of variation in X is the same at every value of Y. So if we're going to calculate confidence intervals for values of R, we need to assume our sample comes from an underlying bivariate normal distribution, which means we're assuming that all X values are normally distributed and Y values normally distributed, and what's more, that we have homogeneity of variance of Y and homogeneity of variance of X. Do we have this in practice? Fairly often we're prepared to make that assumption. Back at the CR page, we generated data sets with a chosen value of R. If I click down here at red 3 rather than red 2, now I can sample from an underlying bivariate normal population that has a correlation between Y and X of rho equals some value that I set with this slider. Here I've set 0.5. And this first sample has a R value of 0.36. If I click again, 0.4. Click again, 0.45. 0.55. 0.49. All with sample size n equals 50. And for each sample, I get not just the R value, but also the 95% confidence interval on that R value. So the 0.61 is our point estimate of the population rho, and this confidence interval is our interval estimate, here running from 0.399 up to 0.759. So as I click, we get a dance of the R values and also a dance of the confidence intervals on R. So watch these values here as I click and take a number of successive samples. As you'd expect, the R values bounce around quite considerably. In the long run, how many of these confidence intervals would you expect would include the population value of 0.5? Yes, of course, 95% of them. And in 5% of cases, perhaps we should display this in red because we obtained a sample whose confidence interval on its R-value did not include the population true value of correlation, 0.5. Now suppose I chose a value of n that was much larger, say 200. Would we expect the R values to bounce around more or less on successive samples? We're still sampling from an underlying bivariate normal distribution with correlation 0.5. Well, they still bounce around, but would you agree not so widely, not so frenetically as before? And correspondingly, of course, we expect our 95% confidence intervals to be shorter when we have larger samples. And you can experiment with a much smaller n as well, and you'll see that these R values bounce around very wildly if samples are quite small, and correspondingly, all the confidence intervals are really quite long. With this big sample from our bivariate normal distribution, I can click Display Marginal Distributions, and I get along here a picture of all these data points collapse down, all the x values collapse down to this dot plot, and here all the y values collapse down to this dot plot. And if I take new data sets, you'll see that those marginal distributions, as they're called, bounce around also. But in every case, we get a bunching together of lots of values near the center and then fewer out in the tails, exactly as we expect from the bivariate normal distribution, in which the distribution of x values is normal and the distribution of y values is normal. So that's exactly as we expect for random samples from a bivariate normal distribution. Over at the one correlation page, I now have a simple figure that shows the 95% confidence interval on a selected R value. And here I've selected sample size of 30 and 95% confidence interval as usual, and an R value of 0.4. Now I can use this big slider here to change R. And I'm going to go up to larger values of R, see what happens to the confidence interval as we approach 1. It gets shorter and more asymmetric because 1 is a fence, a ceiling, and no value of R in the confidence interval can go beyond it, and so the confidence interval is sort of squashed in there. Now I can click at red 3 to turn on the cat's eye picture, and there it is. So a little asymmetric because the confidence interval itself is asymmetric. The upper moe is shorter than the lower moe, and to a greater extent as we get closer to 1. As we come down here towards R of 0, the confidence interval gets closer to symmetric, and there it's entirely symmetric. These two arms are the same length, and if I go down to negative values of R, once again it's asymmetric and getting shorter as we get down towards the floor at -1. Now for an R value of 0.4, let's change n, the sample size. What would happen if n is larger? Of course, this confidence interval will get shorter. There's n of 90 and there's n of 120. There we are back again at n is 30, down to n is 10, and we've got an extremely long confidence interval. In general, confidence intervals on R values are often surprisingly and disappointingly long. If we have a sample of size 30, quite a reasonable size sample in many situations, for an R of 0.4, the confidence interval actually runs from almost as low as 0 up to getting onto 0.7, from 0.046 up to 0.665. Really a very wide range of uncertainty for the underlying population correlation. So for correlations, we really need quite a large data set to have reasonable estimates of population correlations. If you would like to work with p-values, we can click down here at red 4 and turn it on. We can use this slider to set row 0, that's the null hypothesized value of population correlation we're going to test. And for this particular situation with n of 30 and r of 0.4, then the p-value is 0.028, just as we would eyeball by looking at this confidence interval and noticing it's just a little way away from the null hypothesized value of 0. At the two correlations page, you can use these two sliders here to adjust two correlations, R1 and R2, and then on this difference axis you see the difference between these correlations with the 95% confidence interval on that difference. So here we have correlations of 0.26 and 0.64 for these particular sample sizes, 87 and 146, and there is the difference, which is 0.38, and the confidence interval on the difference runs from 0.165 up to 0.605, as you can see on this axis here. So this difference of 0.38 is not itself a correlation, it's a difference between two correlation values. And this confidence interval on that difference is a range of possible difference values between the correlations in the two underlying populations. And just as very often in practice, confidence intervals on correlations are disappointingly long, or even more so, the confidence intervals on the difference between two correlations is often disappointingly long. So if we want to establish strong evidence that we do have a difference between two underlying population correlations, we typically have to have really very large samples or an extremely large difference in correlation before we get a confidence interval short enough to give us reasonable evidence that there is a difference between the correlations in the underlying populations. Incidentally, I must emphasize that this page and these calculations are for two independent correlations, correlations that come from independent data sets. I can finish by going back to the data set we started with and just say again what a wonderful picture a scatter plot is for representing a relationship between an x and a y variable, and how valuable it can be to use this R value calculated from the sample as the basis for estimating the correlation in an underlying population.